We're asked to compare the intermolecular forces between carbon dioxide, carbon disulfide, and carbon diselenide. The most direct way to answer this question is by using the boiling points given. We're given the boiling points of two of these liquids, 125 degrees Celsius for carbon diselenide, 45.6 degrees Celsius for carbon disulfide. And we know from general knowledge that carbon dioxide is not a liquid, it's a gas at room temperature. Recall that intermolecular forces is a proxy to the vapor pressure. The greater the intermolecular forces, the more likely they're going to remain as a liquid, at least in this example, at room temperature. In other words, they're not going to want to vaporize. So the vapor pressure of the substances with the highest intermolecular forces will be the lowest. And because vapor pressure is a proxy to boiling point, specifically, it's when the vapor pressure of a liquid is equal to the external pressure. That means the lower the vapor pressure, the higher we have to raise the temperature for it to match the boiling point. In other words, those liquids or those substances will have the higher boiling point. So this summarizes the relationship between intermolecular forces, vapor pressure, and boiling point. So now let's put these three substances in the order. It's asking us to describe the strengths of the IMFs in order from carbon dioxide to carbon disulfide to carbon diselenide. Now let's label these with the boiling points given. We're told carbon diselenide has a boiling point of 125 degrees Celsius, and carbon disulfide has a boiling point of 46.5 degrees Celsius. And we know carbon dioxide is not a liquid at room temperature, it's a gas. So we can say its boiling point is less than 25 degrees Celsius. In fact, you don't ever see carbon dioxide's boiling point at standard pressure. But we'll get to that when we talk about phase diagrams. All right, so there you have it. From carbon dioxide to carbon disulfide to carbon diselenide, intermolecular forces increase. Because as we said earlier, if a substance has a higher boiling point, it's because it has higher intermolecular forces. And that's what the question is asking us. A second way we could have answered this question is by taking a look at their structures. All three of these compounds have a central carbon surrounded by each of these chalcogens. So the structures are going to look very similar. All three of these molecules are linear and have no net dipole. Now the carbon-oxygen bond is polar because that's the only bond that has a delta chi, or a difference in electronegativity, that's significant. Whereas the carbon-sulfur and the carbon-selenide bonds are fairly equal in terms of sharing electrons. But even though these bonds are polar, there's no net dipole because the molecule is linear and symmetrical. Those dipoles will cancel out. So in other words, all three of these are linear and nonpolar. So when we're talking about intermolecular forces, the first thing we consider is, does that molecule have any hydrogen bonding? There's no hydrogen bonding in any of these substances. The next thing you look at is if there's any dipole forces. And again, all three of these are nonpolar, so there's no net dipole in any of these substances. So the final thing you consider, which all molecules have, are London dispersion forces. And in this case, it's just dependent on the size of the molecule or the molar mass. Now, sometimes you have to consider surface area and other factors, but in this case, because the structures are very similar, you can say the substance that has a higher molar mass is going to have greater London dispersion forces. They're more polarizable. The molar mass increases from left to right, and therefore, because the only IMFs present in these three substances are London dispersion forces, you can also say the intermolecular forces increase in the same order. So we came to the same conclusion using the boiling point information given, as well as the Lewis structures.